Last but not least, finishing up 3.2 and 3.4, we have two application problems. So number 7, consider the function g of x equals negative 2 times x plus 2 squared plus 3. Now graph the function f of x equals g of x plus 5. Okay, so let's think about this for a minute. We have this function. That's our g of x. And they want us to graph this new function, which is f of x, which is g of x plus 5. Meaning we're going to take our g graph or our g function and we're going to move it somehow. Okay? And the question is, okay, well, how are we going to move it? So if I have over here this g of x plus 5, that's a transformation. It's just, instead of being written like we're used to seeing, it's written in function notation. So consider I've got those parentheses and I've got that x plus 5. If you have a movement inside parentheses, is that the vertical stretch and shrink? Is that the left and right? Is that the up and down? And if it's in parentheses, it's your left and right. So we're either going to move this graph left or we're going to move this graph right. And specifically, because it's inside the parentheses, it's the opposite of what we would think, which means take g of x, move left 5. So we can either just go directly there, or we can, kind of graph it and then move it. So I'm going to start first of all with g of x, which I have outlined in red. This is telling me take my function, move it to the left 2, up 3. So typically my vertex is at 0, 0, and I'm going to move left 2, 1, 2, up 3, 1, 2, 3. Then from there, once I have my vertex, I can go over 1, down 2. Over 1, down 2, over 1, down 2. So my function, sorry, that's a really bad graph, would look something like that. But really they want you to graph f of x, which is g of x, the red one, and move it left 5. So we're just going to take the graph and go, okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And for the sake of this problem, you're done, because that's all they wanted you to do. So graph that function, that's the blue graph, you're done. But I want to know, what is that actual function? Like what is it? What's the equation of it? Because the only thing they gave me here is this g of x thing, and I don't want that. I want the actual function. So I'm going to look at g of x in the red box. My graph still goes over 1, down 2 from the vertex. And then I've got my x, and then I've got something, and then I've got squared, and then I've got something else. And this is where knowing vertex form really comes into play. So vertex form, here is my vertex, and my vertex is at -7, 3. So if my vertex is at -7, 3, let's go back and look at this red one here for a minute. Do you notice that your vertex here on the red one is at -2, 3? But in the actual equation, it's +2, 3. So if my vertex on my blue one is at -7, 3, then I'm going to have a +7, 3. And that is the function of the blue one. Last but not least, number 8. Water fountains are usually designed to give a specific visual effect. For example, the water fountain shown consists of streams of water that are shaped like parabolas. Notice how the streams are designed to land on the underwater spotlights. Write and graph a quadratic function that models the path of a stream of water with a maximum height of 5 feet, represented by a vertex of 3, 5, landing on a spotlight 6 feet from the water jet, represented by 6, 0. Okay, so I'm actually going to start with the graph part, because maybe if we could look at the graph, we would better know like what function we're trying to get to here. X-axis, y-axis. Excuse me, sorry. Okay, so let's go here. It says a maximum height of 5 feet represented by a vertex of 3, 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So this is 2, this is 4, this is 6, this is 2, this is 4, this is 6, and we've got 3, 5. 1, 2, 3, up 5. That is my vertex. Landing on a spotlight 6 feet from the water jet, represented by 6, 0. 6, 0. And then we're going to look at this, and we're supposed to write and graph this thing. I want you to look at that and figure out, is there anything else that we possibly could know? Now, we know that the water jet is a parabola. We also know that parabolas have a vertex. And then we also know that parabolas have, through the vertex, this thing called the axis of symmetry. If my vertex is up here at 3, 5, okay, and then I have this other point over here at 6, 0, what do I also know is over here? Because it's kind of like a reflection, so I also know that we're going to have the point 0, 0, which means this particular water stream is coming out of the ground, going up to the vertex, and then going back down to the ground. And again, it should look symmetric. I apologize, I'm not the greatest artist, but that is your water stream. So when it says graph, we're good with our graph. We have our water stream, it's been graphed. But now we need to write the function. The way we're going to start is I'm going to start with vertex form. Because we know the vertex form, we have y equals a times x minus h squared. Don't forget the squared, otherwise it wouldn't be a parabola, plus k. Now, in vertex form, I know that the vertex is represented by hk. And I also know that my vertex is 3, 5. So this must be my h, and this must be my k. So I'm going to go substitute those in, and I have y equals a times x minus h, which is 3, squared, plus k, which is 5. Now, just check. If you've got a minus 3, it really means move over positive 3, and then plus 5 up 5, so your vertex is at 3, 5. So now I'm looking at my function, and the last thing I need to figure out is I need to figure out my a value, which is over 1 something. Now, for the sake of my vertex, I would go over 1, and it's down something. Over 1, down something. If you're thinking go over and then down to 6, it doesn't work like that. For your a value, it always has to be over 1. You can't go over 2, you can't go over 3. It has to be over 1. And then the other thing is, well, we could kind of guesstimate it, but I don't want a guesstimate. I want an exact value. So pause your video, think about it. We got to figure out how to find a. And the way I'm going to find a is I'm going to use another point. I'm going to use this point. And this point is x comma y. And in my equation here, I'm going to substitute my x value and my y value, which will then leave me a to solve for. So x, y. Y is 0, so 0 equals, I'm going to leave a because that's what I'm trying to find, x, which is 6 minus 3 squared plus 5. And then I'm going to simplify this, and I'm going to try to figure out what a is. So 0 equals a. 6 minus 3 is 3. squared plus 5. Then I'm going to do 0 equals a times 3 squared. 3 squared is 9, so this is 9a plus 5. Then I'm going to subtract 5. So negative 5 equals 9a. Then I'm going to divide by 9. So negative 5/9 equals a. And again, just leave it like that. Now that I know that, I have to go back up to my function. And I've got a couple different options. I've got my basic vertex form. I don't want that. There's nothing in there. Then I've got this, which has my h and my k. It's got my x and my y, but it doesn't have a. So I kind of like this one. Or I've got this thing down here that has like a 0 and a 6 and all that stuff in it. Think about what an actual function or equation looks like. And the one we're going for here is right here. You want to go back to this guy. So that guy, I'm going to bring him down over here below my graph, is y equals a. Well, didn't we just find a was negative 5/9 times x minus 3 squared plus 5, and this is the equation that models the water as it comes out of the origin, goes up to your vertex of 3, 5, comes back down and hits the ground at 6, 0. So if we were to graph it using vertex form, the vertex would be at positive 3, positive 5, and out of your vertex you would go over 1 and down 5/9, which is just a little bit more than half, and that would be the stream of your water.